Welcome to our annual general meeting. My name is Ron Petty, and I am the chair of the SFBACM. I'd like to just do a quick recount of the last year before we get into our key event, which is our election, and then hand over to Greg for our presentation. First, thanks to our sponsors. I will be sure to talk to these people again and again and to keep them happy. Thank you very much for your support. All right, so what are we going to talk about? So volunteering. First, what do we do? Content. So we are bringing back the bit dropper. So kudos to Michelle, our volunteer, and Greg, who is helping us resurrect the bit dropper. I looked around and found some dated material. The one on the right is from 1966, and the one here, I believe, is from 1973. And it's just pretty cool to actually see these things way back when. And that there's hints at things that are older, but unfortunately a little hard to find. There's broken links and the like. Now, another thing that may be a little hard to see here is on the left. This is all of our meetings in the last 2 years. We have single-handedly put on more events than the hospitality industry in San Francisco. So kudos to Greg, to Liana, everybody who built, everybody who makes this happen. That's pretty cool to see. Just looking through our titles of our events, we have quite a compelling showcase compared to most of what's going on in town. There's a lot of competition here in the Valley, and you guys do a great job. So keep it up. All right, what else do we do? So we got content. We also have committees. So not a ton of information here. We're not going to spend a lot of time on this. The point here is just be aware we have a lot of things going on with our chapter. The names associated with this is just really a point of contact. This is not the leaders of a particular effort. Maybe they were in the past. This is just if you are interested in these functional areas, come find these people, and just so we can have some kind of organization about it. You can always email us or DM us on Meetup to get a hold and get this information. And we'll share this presentation as well. All right, so we got content, we got committees, we've got community. So why do we even exist? We are the Professional Society for Computer Scientists. This is all about our education, ongoing education, but it's also about kind of giving back to the community as well. So we live in interesting times. Somebody said that before. We're saying it again. We're stealing that. And this is a place where people could not only come to learn. We have Tom, who will be speaking here tonight. We'll learn new things, but we can also share. We try to engage the local universities. I don't want to say get into lobbying and politics, but civil society. Those are the kinds of things we want to do on top of just educating ourselves. All right, and that brings us to our main event tonight. I'd like to welcome Greg Weinstein, former chair, who will help us go through our election.
Hi, welcome to meet you all. My name's Greg Weinstein. I am for 8 years either chair or vice chair, and I'm currently a member at large and a past chair of the chapter. The general membership meeting will only take 5 minutes, and we'll get to our program very quickly. So please bear with us. I thank you all in the room for showing up tonight. This is wonderful. I now call to order our 69th general meeting, annual meeting. I ask for a motion that our minutes from the last annual meeting be waived. Do I hear a motion?
I motion.
I hear a motion. Do I hear a second?
Second.
I hear a second. All in favor?
Aye.
Any opposed? Motion passes. Now for the treasurer's report. I'd like to invite Bill Bruns to give us an abbreviated treasurer's report. Bill has been our treasurer for many years, and we all need to really show our appreciation to him for a great job.
We'll pass that later.
So a year ago, on June 30th of 2025, our total bank accounts were $27,375.08. And as of today, we still have well over 20,000. We have $23,381.86. So
Thank you very much. If there are no questions, let's move on to our order of business for today, which is elections. Is someone here representing our nominating committee? All right, I open our nominations for offices, and a member of the nominating committee will now place our list that our nominating committee came up with into nomination.
I would like to nominate the following slate of candidates. We have our current vice chair, Karthik. Where is Karthik? Karthik? Thank you, Karthik. Vice chair, Venkat. Treasurer, Bill, who's back there working. Our members at large, Greg Mikowski, Greg Weinstein, and Keith Curry. Thanks.
And our past chair automatically, Ron is Ron is replacing our past chair, Dr. Yash Shroff, who is leaving the council. And we thank him very much for his service over the years.
Question?
Yes, sir.
Other than sounding nefarious, what do the members at large do?
They eat a lot of food. So what are all the members at large doing? They eat a lot of food and they grow larger and larger. No, but actually the members at large are both recognition of service and also the people who are involved as committee chairs or other people who are moving the business of the chapter forward.
Thank you.
Oh, you're very welcome. Are there any other nominations from the floor? Do I hear a motion nominations be closed?
A motion to be closed.
I hear a motion. Do I hear a second?
I second.
I hear a second. All in favor?
Aye.
All opposed? Motion carries. So we'll move directly on to elections. I note that as chair of our annual meeting, that we obviously have a quorum in presence. All in favor of electing the slate, please say aye.
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 All opposed, say nay. I thank you. Do I hear a motion that we declare them all elected by acclamation?
Aye, motion.
I hear a motion.
Second.
Second. All in favor? All opposed? No opposed. Our slate of officers for the next calendar year, which starts July 1st, are now members and officers and the people who are running the chapter. We thank everyone so very much. We especially thank the volunteers who are leaving the chapter right now or leaving a position of responsibility, and we thank them for their service. Is there any other business that we need to carry out tonight? Hearing none, is there a motion we adjourn?
Motion we adjourn.
I hear a motion. Do I hear a second?
Second.
I hear a second. All in favor of adjourning, say aye.
Aye.
All opposed? We are adjourned, and thank you for 69 wonderful years. And all the people here get birthday cake. So thank you very much.
Thank you, Greg. Appreciate it. You heard the man. It's cake time. For the next 15 minutes, we will be over here cutting the cake and then on with the show. Okay. Thank you, everyone.
A UFC fight to go with the birthday cake?
Yes.
So tonight's talk is IEEE Mass Storage Roadmap 2026 update. The speaker is Tom Coughlin, president of Coughlin Associates, IEEE fellow, ACM senior member. We are the San Francisco Bay Area ACM. We're a local chapter, professional chapter of the Association of Computing Machinery. We were founded in 1957. Right now, we're eating some birthday cake for our 69th birthday. So that's pretty old in meetup years. We have just a $20 annual membership. You can see our upcoming talks on our meetup site, where we have about 13,000 people that have come to our past events. We have 180 or 200 past talks on our YouTube channel. We have a honor system jar for food in the back. We have a number of sponsors. There's a location sponsor, Valley Research Park. That's where we're located right now. So they have office suites that they rent by the cube or other areas. There's also RXM, Cloud Native and AI Training and Consulting. They offer a variety of training classes. If you need, say, a week-long Kubernetes class custom trained at your work site, they can do things like that. We also have a sponsor that's called Front Egg. Front Egg has an out-of-the-box low-code identity platform. C-Cube, from C-Cube, myself, I'm the Chief of Data Science. We have a couple of products in Teleconnect, chat with your data with RAG, and we're adding Graph RAG to it. Also Guardians, rules for guardrails to protect and implement policies, such as on your agents and different things like that. We just now are launching this week to get on the AWS store, and in a couple of weeks we'll be also on the Azure store, as well as you can get demo trial versions from our website. You can use chat in the Zoom or ask questions. So we're always open to looking for volunteers. I guess raise your hand if you're one of the ACM volunteers, just so you know who to talk to. So there's a lot of volunteers around here that you can talk to if you have questions about anything. Let's see. So some upcoming ACM events. So Monday, June 22nd, here at this location, we have Search 360, from query understanding to LLM enhanced retrieval. In July, we have systems engineering, the role of AI and software in emissions reduction. In August, we have modular test automation and quality engineering in agile systems. We also have an event tomorrow, Thursday evening. Did you want to say anything about that?
In front of the camera here. Yes, tomorrow evening at Intuit, you are required to register in advance, but please come. There will be 3 talks all along the use of agents, from design, maintaining, and kind of the future of agents. So yeah, please come check it out. Free food and drinks and parking.
Yes. Details on the meetup website, and that's also where you register. So I'd like to introduce tonight's speaker. So the topic again is IEEE Mass Storage Roadmap 2026 by Tom Coughlin. He's an expert. An expert group recently completed this roadmap looking 15 years into the future. NAND flash, new non-volatile memories, hard disk drives, magnetic tape, optical storage, and the very interesting DNA storage. He is a digital storage analyst, a business and technology consultant, over 40 years in data storage industry. Coughlin Associates consults, publishes books and marketing reports. He's a regular contributor to Forbes.com and M&E organization websites, and many, many more things. Details are listed on the meetup site. So please give some applause to help welcome our speaker.
Thank you. Thank you, Greg. Thank you, Greg. Let me try to get my talk set up here now. So I gave a talk here for the local ACM chapter, actually, June 18th last year. And there are actually some of my slides that are similar slides to what I gave at that time. But I also got some new stuff because I'm a co-chair of an IEEE Mass Storage Roadmap, which is what the new material that I've got in here. So this actually was an AI generated image. I wanted Prometheus bringing down storage and memory from Mount Olympus. So that's what it came up with. So I'm going to talk a bit about what this process is. This mass storage roadmap, IEEE actually has in what they call their Future Directions Committee. They have this road mapping effort. There's a lot of stuff on semiconductors, but also networking and many other areas as well. And one that I've been a co-chair on is mass storage. So we'll talk a bit about that. I'll talk a bit about some of the drivers of storage, some of the stuff and some of the things you saw before. and then about the different storage technologies and getting into the roadmap for those different storage technologies, hard disk drives, magnetic tape, all the things that Greg mentioned there. So let's get started here. So here's the team that's involved. Was involved in the mass storage roadmap. And again, IEEE actually has a lot of different road mapping efforts going on. They call it IRDS. The semiconductor ones are the most well known. This activity actually was part of something that's called NEMI or INEMI in the past. We actually, from about 2003, Roger Hoyt, who was my partner in doing this for many years, was actually involved before, but we were doing this roadmap about every 2 years. It's something called INEMI back from 2003 on. So we were both co-chairs of this. And so Roger's on he's listed on here as but we also have people from some of the major storage companies, IBM on the tape. We have Western Digital and Seagate. We have Kioxia. We also have folks involved with various optical storage technologies, and as well as in DNA storage as well. So that's the experts that help put the roadmap that I'll be showing you together. And because there's these other roadmap efforts that are going on in IEEE, and some of these are solid state storage, for example, there's connections with the various semiconductor roadmaps. And so this shows some of the other activities in IEEE on road mapping, on lithography, semiconductor, beyond CMOS systems and architectures, CMOS and beyond CMOS. And they had some contributions in Interact in terms of the roadmap we came up with here, which I'm going to talk about. We also had external collaborations. There is a group that's involved in a tape roadmap that did a roadmap for that about a few years ago. So that was and also there's one on hard disk drive in the industry, which is also a few years old. We looked at what Seagate was talking about doing, Western Digital as well, Toshiba, and Spectral Logic, for example. That's also on the tape side of things. So with that, I'm going to go start talking about some of the drivers of memory and storage demand right now. And overall, we need lots of storage and memory. In fact, it's really expensive right now because the demand is bigger than the supply. A lot of that's due to artificial intelligence, and I'm going to talk a little bit about that. There's an IDC projection of a few years ago of 394 zettabytes of data generated annually by 2028, about 3 times that, for instance, in 2024. And much of the stuff comes from sensors, IoT things, and most of the stuff we don't process. Yeah.
That exclude generative AI data?
At the time this was done, I think it probably did. Yeah. Yes. But a lot of stuff, is things we just capture, make decisions real time. And at least before we were trying to train things on everything, we didn't keep all the raw data. Nowadays, that's changing. And the greater use of AI, data centers at the edge and also in various devices, both consumer and industrial devices, is increasing memory and storage demand. And also, of course, power consumption, latency. These are other important considerations. And many times when you're actually building larger systems that are storing information, you have more than one type of technology you're using together. So you kind of have a hierarchy of those technologies. So this leads us to look at all these technologies, how they're developing, how they're going to continue to satisfy the requirements for people to process information, because all the stuff we process lives on storage and memory. So last year at the GPU Technology Conference, Jensen Huang spoke about the plans for 2027, for example, and give some insights into terms of one of the big popular applications where it's GPUs doing AI. This particular one is showing 365 terabytes of fast memory, like the high bandwidth memory, HBM4E, and delivering 4.6 petabytes per second of data rates to the GPUs. So yeah, it's pretty big numbers. And that's why DRAM is really expensive right now because of that. So more recently, and the CES show this year, Jensen gave another talk where he talked about AI native storage architecture, looking at now the inference side of things in particular, this inference context memory storage with their Bluefield 4. So this is AI native. It's a key value store cache to boost long-term context. So when you interact with an AI, as you've interacted with before, if it has enough memory, it can keep track of that. And so it's another memory hog, basically, to be able to do this. And it's also interesting things around this that have developed, of course, like Google talked about their TurboQuant. There's ways you might be able to compress some of the memory, if, depending upon whether that overhead is an issue for you. The overhead of compression, decompression is an issue for you. But this has developed a whole nother layer in this for the inference side for demand for memory and probably also storage as well. Another thing is, and actually I gave a talk on memory and storage and data centers yesterday. I know there's at least one or two people that were at the talk or online or in person. So as we do more stuff, we do more stuff in space, things like interplanetary internet, something that's been brought up before, where you have a store and forward type messaging because you have unreliable connections trying to communicate between various places in space. You have to schedule when you're going to do it. And storage is going to play an important role, of course, there as well. And so if we develop and do more stuff in space, we're going to be naturally doing more computing in space. And that was my message yesterday, which means we're going to have some kind of data processing and all the elements of that in space. And yeah.
Member of the IEEE space data security team that I'm on?
Not that one.
Just check.
What IEEE is huge and sprawling. What's it in?
So I suggested that we use the same format that cell phone companies were using to secure data, because the NSA believes in it. But people think we need to spin up something unique.
So who's organizing this, or what's it on?
IEEE USA.
Oh, USA. Okay. All right. Send me information on it. I'm actually we have a space tech initiative we're getting started in IEEE, our Future Directions Committee. And so we're trying to collect all the space related stuff, that IEEE is doing or wants to do in that. So I'd love to find out about that. You betcha. So Lone Star Dragonfly Aerospace, by the way, that's a picture of their lander on the moon. This one didn't topple over. No, wait. The Lone Star one did topple over because it's top heavy. But they've been using storage devices like Phison provided SSD, a version of their Pascari SSDs for this. This shows the Dragonfly Aerospace Blue Glow lander, which was a squat little thing. You can see it there in the moon. That one did not fall over when it landed, probably because it didn't get oriented badly. There's a Lone Star one, which had this data center module on it that landed, but it's kind of top heavy. It's much longer. Apparently it tipped over, it landed with a bit of an angle and it tipped over. But there's other things going on too. In November 2025, NVIDIA Max startup StarCloud launched an NVIDIA H100 GPU into orbit on its StarCloud 1 satellite. NVIDIA, Google, SpaceX, and just about everybody and their brother are exploring AI data centers in space, although I haven't heard Microsoft talking about it yet. To get around terrestrial power constraints by using solar energy in space, StarCloud plans to build a 5 gigawatt orbital data center with solar and cooling panels measuring 4 kilometers square. So that's kind of a large one. But there's an awful lot of other plans, a lot of them around building constellations, and like I was talking about before, the only way you get rid of heat in space is radiation. So that means surface area. So it actually drives one approach to that would be to build things that are smaller, have less volume, but more surface area as a consequence of that, and that will be a little easier to dissipate the heat as a consequence of that. So anyway, constellations, a lot of companies are talking about that. I think SpaceX said they're going to put 1 million little computing components in space, communicating with each other by lasers, and essentially building a big, not multi-node computing complex doing that, for example. Just one example. Yes.
You're familiar with, my physicist told me You just put a solar panel between what you have on the sun and then heat isn't an issue.
Well, maybe. I mean, your solar panel's still going to get hot, right?
Oh, yeah, you use that energy to run the.
You do, but also solar panels, they like the energy to generate the electricity, but the heat also reduces their yield too. So it's kind of a double-edged issue. So you may have to do whatever it is you're gathering that's gathering the heat. You probably need to dissipate.
Yeah, because if it's 20% conversion,
Mhm.
and 80% is going somewhere.
80% is going somewhere and it's heat, and you don't have any air out there, so there's no convection. That's
So
why.
you need to on the back side, you need a very black, large surface. At the front side, you need a reflector.
And you need some way of moving the heat from one side to the other, so there might be liquids.
There's liquid.
Yeah.
That escapes.
Yeah. Or not escapes. It could be a closed system. But anyhow, so the stars seem to be aligned on creating an extra terrestrial data sphere in addition to all the stuff that's going on here on the Earth. So let's talk a bit about some of these storage and memory technologies. So first of all, this is showed this last year, but basically going from the right side to the right side to the left side here, we're going from faster to slower devices. So DRAM and SRAM, saying a DIMM memory channel, provide very high performance memory and access. If you have a PCIe bus running, say, PCIe 6 even now and 7 eventually, for example, somewhat slower than the memory channel. And so NVMe, for instance, with SSDs runs on a PCIe channel. So they're a little bit slower than the memory because of that. The interface, SAS and SATA interfaces intrinsically are a little slower. So whatever you have with that kind of interface is going to be a little bit lower performance. Hard disk drives are electromechanical devices. And so they actually, because of that, they have some access time and latencies that you don't have, say, in the solid state devices. However, the other important characteristic, which is why, especially if you're building a system with a lot of components, you may want to think about using things together. So this is a chart by a colleague of mine, Jim Handy uses this. And if you look on the vertical axis, it shows a log plot of the bandwidth, basically representing how fast this stuff works. And on the horizontal axis, a log plot of price per gigabyte. So this is cost versus performance, basically. And so if you go in the L caches, usually SRAM type memory, L1, L2, L3, they are very fast, but they're also very expensive. And so you tend to have a little bit of them, enough to make things work for you. DRAM is a bit less expensive, but it's still more expensive than, say, NAND flash, hard disk drives, and even magnetic tapes. So we can compare all these devices here, and you can see, and so when you actually build systems, assuming it's a large enough system, that you oftentimes will combine more than one type of technology together to get some kind of an optimization or trade-off between performance and cost. So that's generally the way, for instance, data centers generally use this, and almost all the data centers in the end have stuff on tape, which it's very inexpensive. When the tape's not in a drive, it's not using any energy basically, except just what the ambient temperature is.
Do they still have to replace the tapes every 10 years or something?
Something like that, yeah. Though, in theory, they could last for like 30 years or so. But in 10 years, you probably get storing a lot less space, what you can store on the tape now, because all these technologies are, developing, getting denser over time. So let's look at the individual technologies again, starting with hard disk drives, magnetic tapes. This is magnetic recording technology. And the hard disk drives are sophisticated electromechanical devices. They can access data from multiple surfaces. They have a rotary spindle motor that rotates the disks, the magnetic coated disks, and with a head that writes and reads information on the disk, which moves around the disk using an actuator motor. So the first one of these was the IBM RAMAC storage unit in 1956, which stored a little bit less than 5 megabytes on 24 2-foot disks. 52 2-foot disks and a pneumatically actuated single pair of heads. Hard disk drives take a certain time to get to data. That's called the access time. And that time is composed of the time to position head over the right location on the disk surface. So the electronic board in the back of the hard disk drive is basically electronics. It controls the motors creates the data to be written on the disk. When this data is passed to the hard disk drive using the interface between that drive and the computer or whatever it's connected to, and it reads back the data from the signals detected by that read element on the heads. The electronics board may also provide encryption for data written on the hard disk drive, detect and react to environmental conditions that could damage the hard disk drive if something wasn't done, and controls the interface between the hard disk drive and the computer it's connected to. They're increasingly used for data center and enterprise applications. They used to be able to get music players with little hard disk drives in them, for example, but you don't do that anymore. So they're increasingly being used in both large arrays of enterprise storage or in data center applications because they're high capacities and lower costs. They're currently available up to 36 terabytes using heat-assisted magnetic recording, which is an energy-assisted recording technology, or shingled magnetic recording where they're overwriting tracks on top of each other to get higher densities. But in the near future, I guess, and I'll wait for that for the next slide. So there's these methodologies that are developing and still developing there, and I'll show you a little bit more detail on that. So here is this ASRC roadmap in the upper left-hand side there. That's actually at this point, I think it's like 2023, so it's a few years old now. Shows projections of the technology in the mid-2030s and moving from a few terabits per square inch on the density of recording on these disk surfaces to over 10 terabits per square inch will enable hard disk drives, for instance, with 10 disks that can achieve 100 terabytes or more in the future. So enabling these advances requires adoption of some of the technologies shown below here. Energy-assisted magnetic recording, in particular now, the most popular one uses a laser to heat the magnetic recording media. So you can have a media that can retain higher density recording than you could without that. Basically, you have to use Curie point writing where you lower the coercivity of this media to be able to write at the densities they're achieving. So also there's multi-layer magnetic recording that people have talked about doing. Two-dimensional magnetic recording, which is something that they use multiple sensors to improve the accuracy of the recording. The other thing, and I'll mention this just a little bit, is going to more disks as well. So this is actually a newer slide from Seagate. They've been shipping these Hammer, the heat-assisted magnetic recording hard disk drives for a few years. In their latest quarter, they said they had shipped over 1.5 million units out of an estimated 12.5 million units in that quarter, with 32 terabyte and 36 terabyte with or without shingled magnetic recording at that time. This year, we're expecting that Seagate's percentage of hard disk drives shipped with Hammer is going to be higher as it goes on. And they showed this back in May 2025. They showed this chart on their laboratory demonstrations and product maturity, showing about 5 years of product maturity from laboratory demonstrations. So this shows, for instance, 40 terabyte hard disk drives by 2026, 50 terabytes by 2028. And then both they and Western Digital have been talking about 100 terabyte hard disk drives by the early 2030s, or actually before 2030 is what the latest has been. And this is from Western Digital, an event they put on what they're going with their technology. And they're doing a few interesting things here to try to achieve, say, up to 100 terabyte hard disk drives. And that includes, they're actually talking about going to up to 10 or 14 disks. So Seagate's using 10 disks in a 3.5-inch form factor. In the same form factor, Western Digital's talking about going up to 14 disks so to get higher capacities in the drive. Yeah.
What focus on this particular form factor? Does it have to do with the speed of sound issues? Is it just like the perfect size? Or is it because that's what everybody's standardized on and this manufacturers have no choice?
Well, it's kind of what everyone's end up using. There used to be a lot more form factors. There's a 5.25-inch form. Yeah.
This one.
Because it's everyone's built their systems to use it basically at this point. So, but they're also talking about increase. They're actually working on Hammer as well, but they also were talking about some interesting things to increase the performance of these drives. In particular, so both Seagate and Western Digital have shown a split actuator, so you can have basically the drive is acting as if it's two different drives with roughly twice the data rate because of that. Another thing that these guys are talking about is actually for a given disk, writing independently on both the uh, 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 for a given disk, and the heads that are kept together to move across the disk, they're right on both sides at the same time. So another way to increase the capacity or the performance of these drives. Now, this isn't so much, it might improve the overall performance of the system, but it's not so much that they're doing this to compete against, what SSDs can do. It's because as you build these humongous drives, unless you increase the performance, it may take you forever to recover a drive or rebuild a drive, for example. So increasing performance is something that probably is going to be absolutely necessary to do on these drives as they get to be these very large capacities, say 60 terabytes or more in a given drive.
More platters, more parallels.
There's more parallelism, more opportunities to, if you choose to do that and you build the channels that can handle that, et cetera, you can have higher performance. Comes with some cost, additional cost, and that's what's always been the barrier in doing that is people don't want to pay more money for the base unit. But at some point, probably, I believe they're probably going to have to do that. So that's hard disk drives. Here's basically a historical shipping areal density. That's the capacity of the disk surfaces over time, going all the way back to Q1 of 2000. See, there's a period of time. Here's the shipping capacities when this is really very high areal density growth. In fact, around that initial time, some of the areal density growth factors were over 100% per year. So every year you could get more than twice the hard disk drive capacity for a given number of disks. Now it's slowed down. You see periods that slowed down here with the introduction of HAMR. We've seen the maximum areal density is climbing up again. So now it's, I think, somewhere in the range of 20-some% growth, cumulative annual growth rate, and probably going to continue that way for several more years because of these new technologies. So that leads us to the actual roadmap here, and this is looking at from 2022 out to 2040. They're actually asked us to do these roadmaps out 2 times, which are very far in the future. And of course, you have to question how well you can project out to that time. But here's the things we're talking about: capacities by going over 100 in 2030s, over 100 terabyte per drive being available. Gradual increase in the number of units being sold to meet demand, which may or may not meet demand based upon current demand. But actually the hard disk drive company has been trying to meet capacity more meet the actual industry capacity more by the increase in the capacity of the individual units versus building new factories. And they basically said that that's their plan. But this gives you a lot of details on the disks, the heads, other channel actuator technologies, spindle technologies, etc. That our group projected for this roadmap. So that's the hard disk drives. Now let's look at magnetic tape. So digital magnetic tape has been used for computer storage since its introduction in 1952. I think it was an IBM a tape drive. It was digital tape drive. There have been many versions of magnetic tape, from open reels, like in old movies, to modern cartridges like these things here. Magnetic tape largely allows sequential access of data rather than random access like hard disk drives or SSDs. So tape uses magnetic recording technology that's similar to that in the hard disk drives, but it's actually many generations below the densities in hard disk drives, maybe 10 years, densities like the hard drives had maybe 10 years ago or more. The read, it writes on multiple channels at once. So actually when you get a tape drive and a tape into a drive, you're writing on all these channels at once or reading. It actually has really high data rates. In fact, they build NAND flash units to be able to support the performance they need for writing and reading information from these tapes when they're in motion. The actual tape recording density using magnetic tapes, again, it's older than it. Modern tape drives include that flash memory also for recording metadata about what's stored in the tape. They can have a file system, effectively a file system on it between the tapes, within tape or between tapes, that they can keep track of that. So there's a lot of sophistication in these actually old technology, but used today. The most popular tape technology today is called linear tape open, or LTO. It uses, again, that magnetic recording technology. It projects, if you look at this is the raw capacity, and they also like to give numbers where they say 2.5 times compressed data capacity. And this is the latest version of this. They're currently shipping this generation 10 product, which has 30 terabytes in these cartridges. or 40 terabytes. Then the 40 terabyte is achieved not by increasing the recording density, but by using a different media substrates. They can make thinner media and get more media on the reel. So they can actually get an additional 10 terabytes.
Question, maybe tilt the monitor back so it's looking more to cover more ground. Or if you're, yeah, that distance, that's good.
Oh, or go with this distance. Okay. So, but if you look at this, and if you have like a every 2.5 to 3 year introduction of new tapes, and you go look at the compressed capacity, sometime towards the end of the 2030s, we may have petabyte tape cartridges. You know, basically, if you go to those numbers. So here's the roadmap that we had for tape. I'm going to go down to 2040. You see the number of characteristics there, data rates increasing, areal density increasing over time. The native capacity by 2040, we're saying 640 terabytes native capacity. And so multiply that by 2.5 times. And that would be the advertised capacity that they like to use for these tapes. So, you know, and again, we've one theme in a lot of these technologies we're projecting they're all going to be able to grow. There's room for technology growth in these areas. So let's look at flash memory and SSDs. So flash is originally extension of floating gate method of manufacturing non-volatile memory. The first type sort of floating gate memory was the erasable programmable read-only memory, EEPROM, was invented in the 1960s, but doesn't really develop until the 1970s. So each memory bit is represented by a transistor. So the NOR flash memory is more like that today. Today, NAND flash technology is a different architecture. You're getting pages of cells that you're addressing. And today, almost all NAND flash use charge traps rather than floating gates to store the electrons, which enable this memory technology. And NAND flash was a planar tech. Yeah. Well, I was just about ready to get into why they went from planar to vertical, which is exactly that reason. As they got down to around 15 nanometers, they're going to be too few electrons that you store in these things, and you lose some over time. So they were, you know, basically you would not get adequate performance in that. So at that point, and this is back about 10 years ago, or more than 10 years now, that the company started to develop 3D NAND flash structures. Where they're stacked, where the cells are stacked on top of each other. And so they had to have semiconductor technology with this incredible etching technology to be able to make these deep cells, and you'd build the deep holes in the semiconductor and build up the memory layers in there. And so Samsung announced their first 3D NAND flash in 2013, but it wasn't shipping in volume until 2016. And by 2019, 3D NAND products are available from all vendors, and 3D NAND production surpassed planar NAND. In 2024, 2025, NAND flash products shipped with over 300 layers, and with QLC SSD capacities of 60 terabytes or higher. In fact, there's been, you know, talk of 250 terabytes or more, but they're also extremely expensive, more than they were back when they first started talking about these, just because demand has been very high for DRAM as well as SSDs, especially in data centers because of AI. The other issue with building up these stacks is that when you first start doing this, you got incredible savings, you know, reduction in the cost by building up a few layers. The problem is you can only make these layers so thin, and the layers take processing time to build. So as you build more and more layers, the actual savings you get on the cost per byte declined. And so now people are focusing more on other ways to increase the density rather than the number of layers, particularly the logical density, how many bits per cell I can retain, things like that. So SSD and flash manufacturers have slowed that layer increase. And basically, I'm just talking what this slide says. Increasing this, other ways to continue to decrease the cost per bit are to decrease the cell sizes, decrease the spacing between cells, building associated logic in separate wafers, so they don't use the same wafer for that, and then attaching the wafers. So this is getting at that hybrid bonding. and particularly increasing the logical density with more bits per each memory cell. And this actually was some forward insights data. I guess they can't hear me here. Forward insights data that's showing the market size that they projected from 2013 out to I think it is 2026 there. You can see 2026, the market size is very large, but there was a period 2022, 2023 when it was not so, and that actually was true of almost every type of storage and memory technology out there. So the current humongous demand is a big contrast to the way things were basically 3 years ago. Let's see. So here is a roadmap summary for SSDs, and this actually came from another part of the semiconductor roadmaps that were being done in the IEEE. So we borrowed that in our report. But they're the dominant storage media now for client and high performance applications. They're used as primary storage for enterprise and data center. So the image on the right are projections for the NAND flash out to 2037 for the most recent version of that roadmap I could find. And that projects NAND flash with up to 24 bits per die and over 1,000 layers by that time. So, but we'll see, whether you get to those number of layers or not. There's some other interesting things that have been going on. First of all, there's DRAM and static random access memory, which we mentioned before. They're both volatile memories, and when the power turns off, the data goes away. DRAM requires regular refreshes, and actually it is one of the biggest users of energy in a lot of computing applications. It's just refreshing between moving data around and refreshing DRAM. Some of the biggest consumers of energy. And scaling for SRAM and DRAM have slowed down considerably from what they used to be, and they use more power than non-volatile memories. So there actually are some interesting opportunities there potentially for volatile memories to play roles that formerly SRAM, or today SRAM and DRAM are primarily used for. And there's some interesting developments in that at the FMS conference last year. SanDisk with SK Hynix announced that they were working on developing this high bandwidth flash. Basically, it's high bandwidth. It looks like a high bandwidth memory with DRAM, only they're using flash in there. It was building this as a supplement to the DRAM memory. So there's work going on in that area, which is a interesting development for the NAND flash. The other thing is they're also at the conference. Also, there's different ways which you might be able to architect NAND flash technology to get higher performance. For example, with smaller block sizes, they were able to get much higher data transfer rates. You can see that in this upper left-hand chart here. And also architectural changes like one they call storage next, using smaller blocks and optimizing error correction, and GPU computation around small data. PCIe 7, the next PCIe generation, will also help on the performance. And you can see this idea called storage next, where they potential of getting very high data rates out of these drives versus today's SSDs. So there's possibilities of building supplements to DRAM that might use this SSD non-volatile memory, or NAND flash non-volatile memory. So a few observations at hard disk drives and SSDs. I've referred to this before, but right now they're in very high demand. A lot of the manufacturers of, say, hard disk drives and SSDs are sold out. The hard disk drive guys saying they're sold out to like 2027 with contracts to the major data center companies, hyperscalers. So they're in high demand, they're at high prices because of the need to store data that supports training and inference. And the same is true actually of all these digital storage and memory technologies. In fact, I was at the NAB conference a month and a half ago, National Association of Broadcasters conference. There were a bunch of tape guys there, and they're saying they're actually getting demand increase in tape because people are offloading their hard disk drives to the tape, so they don't have to buy more hard disk drives. So it's trickling down in the whole hierarchy. The enterprise, sorry.
StoreNet still
It's not the only one, but yeah. enterprise SSD saw contract prices increase 80% in 2025, and actually spot prices, I heard this a few months ago, there was somebody did a survey. It was something like 20 the dollar price of memory and NAND flash, the SSDs versus hard disk drives, something like 20x. It had been down to like 5x, maybe a year ago or so. Hard disk drives also seen increases. Data demand is still increasing. NVIDIA Rubin and some of these others we looked at is supposed to increase token generation by 10x over the prior Blackwell systems. That increases the more data and AI training. All these things are calling for more demand and ways you might be able to mitigate that. Oh, yes.
So, it's forcing a move to QLC. Is that where each storage unit stores 4 bits?
4 bits, yeah.
And what are the implications of that move to QLC?
It means you are going to have to be very careful on your wear management because your cells wear out faster. It's one of the big implications. It also reduces performance because there's more overhead to recover the data, more error correction. You're splitting up the ability. You're storing 4 bits where you probably used to store 1 bit, for example, or 2 bits, right? Oh, I'm sorry. So the question was about the QLC flash. What are the implications of QLC flash?
And what are the implications of that on the lifetime of an SSD versus hard drive?
So it will likely reduce the life of the SSD, depending upon how much you exercise it and how good your wear leveling mechanisms are. And so it gets you more capacity at a lower cost, but there is a cost. There's performance and life costs that come with it. And so people have to, they're doing what they can to extend that. But that's, a lot of what going to these like 240 terabyte hard SSDs with QLC flash. They have a lot of it there. So the argument might be, depending on how you write on it, it may last a long time because even though the cells may only last, a couple hundred write cycles, it'll take a while to go through all of those. But it all depends on how you use it. So does that help? Yeah.
Talk about CMS, composable memory systems. Can you just explain what it is? I hear it a lot. Composable memory systems.
Composable memory. So I think first you have to decompose it.
Can you repeat?
Oh, so the question was about composable memory system. I think what you're talking about is this idea of breaking up traditional computer architectures into their pieces and then using in their pieces, building those piece components as pools, and then using software to make a machine essentially that has whatever performance, memory, other characteristics you have by allocating these pools to those machines. I think that's a composable memory that you're talking about.
Pools of CPUs or pools of memory?
It can be pools of any of this thing, but in the case of memory, it's like I can allocate memory to different applications or different virtual machines. I think that's what you're talking about. Yeah. Okay. So I did that. So here's my projections of shipping storage capacity, tape, hard disk drives, and SSDs. And let's go into the optical. Sorry, did you get your picture? Okay, optical side. So there's optical disks been used in archive systems for years. A competitor to magnetic tape. There have been many approaches to optical storage over the years, many using conventional looking optical disks and drives. Examples of that are the archive disk that Panasonic and Sony had. Photonics, which is talking about building multiple layers of optical storage layers on a disk. And also a company out of Australia called Optera, which is using a method of creating storing wells of basically they call them burning spectral holes. They're basically changing the emission characteristics at discrete frequencies to different depths, and they can use both those multiple frequencies as well as the depths to encode information. And so they're talking about doing this on a conventional optical disk format. But they're also some tape-like systems. There's a company called Pickle Film, PIQL, out of Europe is doing that, and also Dots 42, which is an outfit down in LA. There's volumetric recording technologies. Project Silica and S Photonics are doing that, and also writing on sheets of ceramic on glass, like a company called Cerabyte. You might have heard some of these companies in the news recently. So here's some images of some of these things. So many startups. There's actually something like 5 or 6 startups now in optical storage right now, which is kind of interesting. I mentioned before about using conventional optical discs here, but also there's S Photonics records in the volume of a quartz crystal. And actually, in my other talk, I was saying that both one of these space missions, I think it was a Lone Star one, was bringing up a S Photonics crystal with Chauvet cave paintings from France, 32,000 years old, images of that. Cerabyte records an array of patterns on a black ceramic layer on a glass substrate. And on the left there, they've shown some demonstration of a concept that they could actually put this in something that looks like a tape cartridge and fit it to a tape cartridge library. For example, multiple, like 10 sheets of this. It's a glass coating with a black ceramic that they then use high-powered lasers to build something that looks like a QR code on it. And by the way, use the high-powered lasers also for the S Photonics to record inside of the volume of these quartz crystals. So here's an optical storage roadmap, the best information we could get on at least some of these technologies here. So the BDXL is that Blu-ray optical storage technology that Panasonic and Sony had for a while, but it's basically not developing any further. I'm sorry, that's the archival disc. Then the photophotonics is shown there as photonics, and also Cerabyte in terms of their projections of what they can do. Of course, none of these companies have anything in mass production yet. There's some special applications for some of these. Yes.
The archival disc, is that Blu-ray?
That's a Blu-ray. Yeah. And they were able to get up to 50 terabytes. The roadmap had 100 terabyte per disc capacity, but they never achieved it. So, basically it was a conventional type Blu-ray, a little bit of tweaking on the lasers and other things.
Are any conventional disc formats that are compatible with conventional disc players and readers? Archival, that is, the recording will last 45 years or more.
Yes, a lot of these recordings will last for maybe 100 years or more. Oh, the question was on the longevity of the actual recording and the media, right? So the recording and the media could probably last 100 years, right? Or more, possibly. Especially with the optical recording when it moved to inorganic materials, because the organic materials sometimes got fungus and stuff. So yes, you can get it to, but the problem, here's the big issue on long-term data preservation is, will you be able to find something to read it back in the future, right? And that's both the interfaces, it's the technology, things like that as well. And that's a whole nother talk to get into. Yes, yeah.
Try to read a 5 1/4-inch disc today.
Yes. Well, in 100 years from now, will you be able to find a USB interface? I don't know.
Not the cord.
Not the cord, exactly. So let's get into DNA. All right. So DNA is really interesting because it's how our information is stored. So it's very dense. It has a theoretical raw bit density of 1 million terabytes per cubic millimeter. Another interesting thing about DNA is when you write it, you don't just write one, you write millions. So if you're into replication, this gives you lots of replication. But it's really slow on the write and read. The theory that people have that are into this is that because we're doing genomic medicine, and we're going to learn how to reduce the cost of doing that, it's going to make us be able to do faster reads. And perhaps if you do, genetic interventions of various types, faster writes of genetic information, that could be then used as a storage media, and the cost would go down. So that's kind of what the basic premise of the DNA storage is. It's very durable. In the right conditions, especially if it's dry and not wet, it can last an awfully long time. The people pull out DNA from, mastodons and woolly mammoths, from the tundra in Alaska and in Siberia, for example, So what is it? Deoxyribonucleic. Yes.
They think it's from.
No.
It's a stuff. It's a chemical. It's a chemical. It's a chemical that's used to store genetic information. All critters' genetic information. So anyway, so a little bit on this. There actually is a group called SNIA, Storage Networking Industry Association, what it used to be about, but it's actually a storage industry trade association. And they have a group that's a special interest group working on DNA storage. It's been very active. They've established DNA bio industry, but it's established, there's established DNA bio industry companies as well as startups who are working on synthetic DNA. Twist last year spun out its DNA storage effort with a $155 million investment. Encoding is done with the bases in synthetic DNA strands. So this is not supposed to be used in creatures. Yes.
Just as a ballpark, like if I want to back up 10 gigabytes, how long does that take to write?
Oh,
Repeat.
the question was if I want to back up 10 gigabytes, how long would that take? I do not know the actual numbers on that, but a fairly long time. Yeah, probably hours, you know. But, you know, I may be wrong on the actual number, but it takes a while. So the two most common approaches are recording by sequencing by synthesis and nanopore sequencing, where they have little holes in a nanostructure, and the DNA strand pokes up and grabs more bases and builds up that way.
So, question for you.
Yeah.
DNA, right? How do they protect it? Because it can be attacked. Like raw DNA doesn't survive very well with attackers, like viruses. And
Oh, well, for one thing, well, so the question was, I think, is there things that are going to eat DNA?
Yeah.
Or destroy the DNA? The biggest enemy to DNA is moisture and is moisture. To some extent oxygen, but the biggest thing is moisture. So one of the tricks of keeping DNA for a long period of time is drying it out and putting it in a hermetically sealed cap. And so Atlas, the company that spun out, from Twist, they've shown these little vials that they say have got a whole bunch of DNA in those things. So it's not so much they're getting eaten or other creatures are going after them. And it is a synthetic DNA. It's not supposed to be able to do anything for life, but the biggest issue is more the, environmental issues.
yeah, DNA tends to fold over. I'm just wondering, it can take it offline.
Sure. Yeah. And if I don't know the answers, I know people that do.
Replication helps.
And oh yeah. Well, the other thing is replication, especially if you're trying to recover data, and lots of copies keep stuff safe, for example. Yes. So there's a number of companies exploring this. They include Atlas Data Storage that's spin out from Twist, Iridia is another company, BioMemory and Catalog Technologies. Actually, BioMemory recently bought Catalog. So last thing here is non-volatile memory. So leading edge processes you can't use NOR flash. NOR flash is a memory that's used for a lot of code storage, say in devices, things of that sort. SRAM it also is having trouble scaling. There's some use of some of these new memories in enterprise applications, and growing number of them in embedded devices built by the major foundries for consumer in some industrial applications. And they're also, as you get more of them using these new types of memories, which eventually might replace even DRAM or SRAM, for example, the price will go down. And that's the big trick, is getting the volume up to get the price down. In fact, NAND flash was more expensive than DRAM until about 2004 or something like that, when the volume of NAND flash grew large enough that it actually became less expensive. So volume is the name of the game. So getting into niche markets and getting growth is a way that these things will become more popular. Now they're interesting because they're fast, they're low power, they're less messy than flash. They don't have the write penalty, the long write times that it takes with NAND flash because of its architecture. NAND, in general, it takes a lot of 2 cycles to erase and write data, NAND flash, and you don't have that with these memories. So here's some of these memories. They're various types of non-volatile memories are available. for a lot of potential applications, including possibly as elements in chiplets or heterogeneous integrated structures. They're magnetic random access memory, or MRAM, resistive random access memories, or ReRAM or RRAM, phase change memories like Optane was, remember Intel's Optane, and ferroelectric random access memories. And they're all single element cells. They only have a single transistor, or in some cases like Optane, a single capacitor. And oftentimes that particular structure is what defines the size of the memory cell versus anything else. They promise to scale past DRAM and NAND flash, so eventually they may be replacing these, especially this in space. They may be attractive because many of these are radiation hard. They write in place, there's no block arrays, more symmetrical read write, and they're persistent. So when the power goes off, the data stays in there. So here's the projections that a colleague and I have in a report that we do, which I actually have. If anyone's interested in, I have some little flyers on that. For embedded memory replacement of NOR and SRAM by new memory technology, one of these new memory technologies, discrete memory, DRAM, NAND, a little later on, and then memory chiplets and things of that sort, even a little bit further on. So, but in the meantime, they're building up volume, they're building on applications, and there's a lot of stuff going on there. And we talk about this in our report, Jim Handy and I. It's over 300 pages. It goes into great depth in all the developments, all these memories, how they work, and how they're being used with a lot of tables and figures. And we also talk about the capital expenses of building these memories as well, and how that will grow. So I also want to let you know, I'm involved as general chairman of FMS this year, which actually has new owners. It's going to be August 4th through the 6th at the Santa Clara Convention Center. It's looking at all the different memory technologies like those I've talked to you here. And in summary, data storage demand is exploding. It's incredibly important for all the different things you want to do with AI, for example. And computer architecture are developing support demand for these massive processing loads, and that's driving developments, all aspects and use of these different types of storage. Hard disk drives, magnetic tape, use magnetic recording. We're talking about 100 terabyte hard drives by 2030. The magnetic tapes are 30, 40 terabytes now, and they'll be growing more in the future. And actually, there's an enterprise tape that IBM put out that I didn't mention that has up to 50 terabytes in one of that size cartridges. So new developments in optical and synthetic DNA, as well as SSD technologies. And embedded applications are driving the growth of a lot of these non-volatile memory technologies. So with that, I want to thank you for the opportunity to come and tell you some more stuff about what's going on in storage and memory.
We did have one Q&A from the crowd.
Okay.
Online crowd. Maybe read it off of the.
Okay.
Let's see. Here we go. Where's my screen open?
Has a significant increase in capacity and areal density required new technology, or is it just improvements and refinements of prior generations? Both. And again, they may be talking about SSDs, I'm not sure. For instance, in hard disk drives, this hammer, although people have worked on it for like 30 years, only recently has there been products that have been able to produce with this, say, in the last 3 or 4 years. And so it's basically, it's a new and a not new technology in a way. It oftentimes takes a long time for things you work on to finally, bear fruit and be useful. In the case of SSDs, they've been doing a lot of things to try to increase the capacity capabilities they've had. They're still going to try to be building up more layers, but again, the cost reduction from that layer count increase is declining. So they have to work on different approaches to it. And some of these ideas have been around for a while, but we're pushing things, even if it's something we've done before, we're pushing it to extremes that we've not done. So in that sense, that it is a new technology, or at least a new, a new face on something that pushes something beyond what we thought we could do before this time.
Well, no, one more.
Okay. When it's time, is NOR flash suitable for terrestrial applications? Yes, actually, NOR flash is the code storage used in all kinds of things. So It's very much used, and it's being gradually replaced by magnetic random access memory and other types of these new memory technologies. Because NOR flash doesn't scale below 28 nanometers. Yeah. Yeah. Yes.
What they call it, memory wall.
The memory wall.
How to break it.
How to break the memory wall. So the memory, what's that?
How to break it.
Oh, the question was, how do you break the memory wall? So first of all, we should say what the memory wall is. And basically it is that I can't get the data fast enough, right? And so the way, what can you do to provide data to the processors as fast as they can use it? And those are the various technologies people use. For instance, they put memory right next to GPUs to try to help, right? The high bandwidth memories and stacks of them. They're talking about putting this high bandwidth flash in addition next to the high bandwidth memory to try to feed the high bandwidth memory with the memory it needs to do the stuff it needs to do. So it's basically the way you deal with it is with architectures and technology developments and components.
How about using computing in memory?
How about using computing in memory? Well, yes, of course. Another big trend that is going on is not moving data around, trying to process it where it lives, which would mean near or in memory. And so there's a lot of activities that go on in these areas. There are some that are more, far out there, like neuromorphic processing and things of that type. And there's others that there is a lot of activity going, a lot of standards activity going on, for instance, in doing some processing with special domain-specific processors do particular things that are in or close to memory. And so that is becoming pretty common a methodology now. It does encryption. It might do compression, decompression, things like that can, so you don't have to do it on a CPU or a GPU. So we're getting a lot more domain-specific processors now doing a lot of domain-specific stuff than has been true in the past.
You do it in memory, you go to this in memory.
In memory or close to memory. Yeah. Yes.
Have recent changes in market economics changed the probability of Optane ever coming back?
Optane, yes. It was kind of a shame, So, we have things like CXL, which are kind of the child of Optane because they were trying to build something that they could have the shared lower cost memory, or they want it to be lower cost memory, but it's this volume thing. So the big issue they ran into, and this is kind of like the lesson of this, they spent $10 billion launching, we estimate something like $10 billion launching, trying to get this technology out there, but they could never build up the market to get the volume up to where the costs were below their cost of manufacturing. They were selling below the cost of manufacturing to stay competitive to DRAM, but they never could get the manufacturing volume enough to drop their cost below what they're selling at. And eventually they decided that wasn't a good business. So phase change memory has not gone away. There are people that are using phase change memories today. And let's see, ST Microelectronics, I think, has some MCUs that they're building that are using phase change memory. And let's see, SanDisk made some noise last year that sounded like they were talking about an Optane-like thing, but I haven't heard anything about that since. So it's possible phase change memory could return. It's one of these viable new memory technologies. Optane was a noble experiment, and we have good things that happened from it, but it didn't return much of a profit to Intel.
So Intel also had the corner on NAND flash memory, and they decided a few years ago that there was no future in it. It wasn't profitable. No one wants to buy memory. It's commoditized. It's not worth it. They sold it to SK Hynix.
They did, yes.
And look what's going on today.
And it's called Solidigm now. So, but yeah, it's part of SK Hynix. Well, 2022, 2023, all the memory and storage companies were hurt because there was all this inventory that people build up during COVID to support builds outs of data centers for remote work. And then all of a sudden people weren't doing that anymore. And they also bought extra stuff because the supply chain was so screwed up. So you bought more than you needed because you didn't know whether you get it or not. And so people ended up it took about a year and a half to 2 years to burn off all that inventory. In the meantime, no one was selling much of anything. And now it's it's just the opposite. Yes.
Memory cost, wait now.
No, not now. Now it's going up. Now it's, and the price of these companies that make this stuff is what Micron's $1 trillion, people are talking about $1 trillion value for Micron. I mean, it's crazy what's going on right now.
Can I interrupt just a minute
Sure.
and give out a door prize?
Oh boy, lights.
We give a door prize of some kind to our attendees who are members. And it was after 8 o'clock, so let me go ahead and give it out. Does all the people with red badges have their door prize ticket? All right. So everyone has their tickets.
Everyone. Yeah,
Yeah. All right.
I don't know what.
Do you have a red badge? I can't see from that far away.
Use.
Blue badge. No, only members with the red badge.
Ah,
Sorry. Would you go ahead and draw
Sure.
a,
yeah, hold on a second. Boy, these are, they'll
they're caught in the bottom.
give me that one back. Okay. All right, I'm gonna read the last three numbers. That should be good enough, right? 0, 9, 0. Do we have a wiener?
Off by one.
Off by one.
off by 2.
0, 9,
That's on
0.
your stat number.
Unless they left already.
090.
Yeah. Do we have to draw another one? Okay.
We will
here we go.
draw another one.
These guys are hard to find.
Someone's going to get this really nice backpack.
Oh, is that what it is? Oh, okay. All right, here's the next one. It's 092. You said you were 2 off. That's you. You get this thing.
Oh, thank you for coming. So tonight we had cake, we had pizza, and we had door prizes. Thank you, everybody, for coming.
Thank you.
Can you stay for a few minutes to answer any questions
Sure. Yeah.
or meet with people one-on-one?
Yeah.
Thank you very much.
Thank you.
Well done.
Do we need to do anything to sign off of the
I think we're good. I think we're good.
Exit. Okay. So I'm going to stop